Welcome to the IEEE 5G Transmissions Podcast. Podcasts with the experts. An IEEE Future Directions digital studio production. In this podcast installment, Alex Wyglinksi speaks to how 5G can be used with cognitive radio and vehicular dynamic spectrum access to support large-scale wireless communications between autonomous vehicles. Alex is co-chair of the IEEE 5G Community Development Working Group, is president of the IEEE Vehicular Technology Society, and a full professor of electrical and computer engineering at Worcester Polytechnic Institute.
What I'm going to be talking about for the next several minutes is the need for 5G technologies applied to the automotive sector. Why is this? Well, there's been a lot of talk in the automotive sector about connected and automated vehicle systems and networks. The idea that we have vehicle platforms that are connected to each other, exchange information with each other in order to make accurate and real-time decisions, especially if the vehicles are either semi-autonomous or fully autonomous. In other words, there's no human drivers operating these systems. And why is this important? Well, what we've been seeing over the last 36 months is a significant increase in research and development work in autonomous vehicle technology. We're beginning to witness prototype systems being deployed on the streets of places like Silicon Valley in California and Singapore and in Boston, Massachusetts. And that auto manufacturers are now promising to consumers that new vehicles with autonomous capabilities will be hitting the roads in the next 5 years. This autonomous vehicle boom, what we're witnessing right now, is no accident. This is building up over the past several decades, and only now are we beginning to see sort of the alignment of various stars that are now giving rise to autonomous vehicle technology. This is especially true given that we've seen many advances in areas like control theory, in sensors technology, in artificial intelligence, and embedded systems. And all of these systems, all these technologies, all this knowledge is now being applied to the automotive sector, right? And as a result, as opposed to, let's say, vehicles 20 or 30 years ago, right now we have vehicles that are very much aware of the surrounding environment that they're operating in. And as a result, because of this heightened situational awareness, we can actually have vehicles collecting all this information around them, make real-time decisions, and then act upon them, which is quite extraordinary, especially when we don't have human in the loop. So as a result, what we really need to do, so this, looking at the autonomous vehicle sector, the big push, what we're seeing over the next several years, is to make this technology reliable enough such that these platforms can operate on the roads and coexist with human drivers when there are no humans operating those vehicles themselves, right? It's also expected that these autonomous vehicles, like there's been a lot of promises that these autonomous vehicles will be safer than those vehicles operated by human drivers, thus reducing the number of automotive fatalities and accidents. So all this talk, what I've been talking about for the next several minutes, what you see in the press, what you see auto manufacturers promising, you might say to yourself, okay, we're done. There's really nothing more we can do in this area. Well, now that's sort of true. Like we're seeing quite a few advances that are being applied to the automotive sector from places like the control theory perspective and the sensors perspective and the artificial intelligence perspective. But there's still more that can be done. So at the moment, we see these vehicles, they're getting information, they're acting upon it, and there's a decision-making process that's constantly learning and continuing to fine-tune itself. But the actions that these artificial intelligence decision makers make, right, and how they implement it in the various forms of controls on these autonomous vehicles really is truly dependent on the sensor information that's gathered from the environment around it, right? And so, at the moment, like most people would say that autonomous vehicles would more or less gather information from vision systems, LiDAR, and or radar systems, either individually or combined together. But there are some limitations with respect to each one of those sensors, which I'll talk about in a few minutes. What happens is a lot of people are beginning to realize that in addition to these sensors, that wireless information, exchange with the vehicles, as well as exchange with, let's say, some cellular base station that's connected to the internet, would provide quite a bit more, almost like a game-changing amount of information, sensor information about the environment around that autonomous vehicle to enable it to drive even more safely than they do right now. Okay, so this kind of leads to the argument that we really do need these autonomous vehicles to be reliable and accurate, and the only way that they can operate in a manner that's safe is that they have a large amount of reliable information that's steadily streaming into them, either from the car next to it, all the way from a cellular base station that says this is what traffic looks like on the other side of town. And that information also needs to be real time. So I mentioned several other sensors technologies that provide that situational awareness right now, and what the community, the automotive community, is turning to in order to enable reliable automotive platforms that can drive autonomously. I talked about radar. And radar is fantastic, don't get me wrong. Radar is a mature technology. We already use it extensively in automotive platforms for things like collision avoidance systems and the like. And it's very robust. There are very few operational environments that would inhibit radar systems from operating properly. Like, for instance, if you had like crusty ice on the surface of your bumper that has a radar system, that may or may not inhibit its performance and the like. And it's a mature technology and it's great. However, radar only sees as far as the first object, which is usually the vehicle in front of it. Vision systems, same thing. Very mature technology. There are plenty of signal processing and image processing algorithms out there to perform things like object recognition. Similar problems to radar. It can only see the environment immediately around it. It doesn't really have beyond line of sight capabilities. Now, LiDAR has been very popular lately. People have looked at it and said, wow, this is great. This gives us like sort of three-dimensional depth of the environment around us. It's not just sending out like, a signal and then saying, oh, there's an object there or not. LiDAR is kind of a game changer in its own right. And it hasn't quite matured yet. There's still a lot of work that needs to be done to make it truly reliable and guaranteed technology. So it has a lot of potential in characterizing the environment. But the problem with LiDAR is very high costs. Like right now, LiDAR systems are on the order of thousands of dollars if you want something that's 3D LiDAR based. Also, it's limited by environmental factors such as rain and fog, which is quite unfortunate because those are kind of the environments we really want autonomous vehicles to drive very, very carefully and safely in, and they really will require environmental information to make the right decisions. So, in all three sensors, I mentioned the same thing. None of these systems go beyond line of sight in terms of their capabilities to gather information about the environment around it. So what we need is a technology that can get that information without necessarily having to look at it and unable to look past, let's say, immediate objects. So as a result, in addition to these three sensor technologies and all of them gathering only line of sight information, there's another issue, and that is the one of data fusion. Data fusion is, like a lot of people have recognized, is extremely vital for safe operation of automated and autonomous vehicles. The main reason is if, let's say, one of these sensors fails or gathers information and kind of reports the wrong thing or is interpreted incorrectly, you need some sort of backup. So it's nice to have some sort of redundancy where you have two or more sensors gathering information about the environment around it. And let's say there's something questionable, like let's say the LiDAR picks up an object that's not there. The radar and the vision system would say, oh, hold on. there's actually an object there. There's no object there, but the LiDAR says yes, there is. And then it's up to a data fusion algorithm, and the decision makers say whether indeed there is an object there or not. So having multiple sources of sensor information coming into the system is actually quite important, because that gives us a little bit more buffer in order to determine what the environment looks like around us and kind of iron out any potential for error that might come up when collecting this data and sensing the environment around us. Okay, but this, of course, creates its own problems. First of all, the quality and the time alignment of the radar data might be completely off of that of the LiDAR data or the vision data. So in order to do data fusion, you have to have proper time alignment of an event, of this surrounding environment, such that we see the world from these various sensors at the exact same time. And that the resolution, the quality of this information is also relatively the same. We don't want really poor vision data, but really great LiDAR data, and then we're kind of in a conflict of saying, oh, the vision system sees this, but the LiDAR system sees that. Because then the comparison of the two, knowing which one's actually accurate or representative of the environment around it, now becomes a little bit more challenging. Okay, so we've seen sort of conventional sensors used in autonomous vehicles, and we see also their issues in terms of how we fuse that data together and the physical limitations of how far they can actually obtain information of the environment around it. So, because of this situational awareness question of the operating environment and how challenging it is, there is a game changer, and I would like to advocate that wireless connectivity, the ability for an autonomous vehicle to gather information from other vehicles, from roadside infrastructure, and from a cellular base station is a game changer. It is another form of sensing technology. Okay? And it can be traded as a sensor. It's yet another source of information that feeds into a data fusion algorithm and the decision maker for the autonomous vehicle to make like some sort of call, saying, there's a truck ahead. Should I turn? There's my exit, but there's a backlog of cars on the off-ramp. There's ice on the road. Well, what happens is you get the same type of information from a vehicle collecting wireless information, like potentially from other sort of sensing technologies. And even more so because in the wireless communications world, we would say that this technology, this sensing technology, has beyond line of sight capabilities, BLOS, where what happens is we can get information from other vehicles that are half a kilometer away, and the radar, the LiDAR, the vision systems don't see anything. They can't go past the vehicle immediately in front of it. At the same time, if we can reduce the latency in the wireless links between vehicles, between a vehicle and roadside infrastructure, between a vehicle and a cellular base station, we could get the real-time information for that vehicle to ride in traffic and perform maneuvers that really require highly reliable and very low latency and almost instantaneous actions. So this is where 5G comes into the picture. Okay, so 5G technology can be broken down into various types of interactions with a vehicle that is driving in an autonomous manner. We have cellular connectivity, sort of like what we use, 4G like anyway, and 5G would just, in that regard, would be just an extension, where we have our smartphones or our interactive vehicle or the vehicle itself, forget about any human interaction, would gather information from a cellular base station that would report out to it about what traffic conditions are like on the other side of town, like on the highway for the next 20 kilometers, 30 kilometers. Okay, so we can find from the internet through that cellular connectivity, through 5G, things like traffic conditions, weather reports, traffic routing, if we need to have sort of like coarse-grained routing of my vehicle, of your vehicle, of that autonomous vehicle from point A to point B. This is what I would like to call macroscopic environmental or situational awareness of the autonomous vehicle. Where what we're looking at is information that is given to the vehicle that's on the order of tens of kilometers in all directions. Now, we also have vehicle to infrastructure and vehicle to vehicle, or V2I and V2V technologies. V2I, or vehicle to infrastructure, are things like where the vehicle communicates with roadside infrastructure and units, things like electronic tolling for highways, electronic parking, smart intersections where we have intelligent lights that change colors to allow optimal traffic flow through an intersection. And so that tends to be more on the mesoscopic, something on the order of 1 to 2 kilometers, where the vehicle might be approaching some sort of smart city or smart road and then it interacts with that road in order to optimize its operation and that of all the other vehicles surrounding it and other vehicles sort of coming within range of that vehicle. Okay. The V2V, this is the holy grail, if you will, of wireless connectivity. The V2V, or vehicle to vehicle communications, is when one vehicle communicates with another vehicle and shares with it information, most likely, its real-time driving capabilities. So suppose that several vehicles are driving in some sort of formation, and then one vehicle is passing them on the left. Well, V2V would be, instead of going from vehicle to cellular base station back to vehicle, because we want to minimize. Latency is critical. We need to minimize that. What we would have is the vehicle that's passing would communicate directly with those vehicles driving in formation saying, hey, I'm passing you on the left. Do not do any maneuvers that would cause a collision with me. I'm now approaching your location in 5, 4, 3, 2, 1 seconds. So what would happen is this is where, in this case, information would be exchanged with extreme low latency. Okay, it would be real time and would be very time sensitive and extremely vital for the sort of like second by second operation of every one of these vehicles. So things like driving maneuvers and driving information and how all these platforms would interact with each other on a stretch of road of 1 to maybe 300 meters long. So in the community, we often look at operations such as lane changing. Lane changing is actually quite challenging and relatively dangerous. If you drive on a road, that is an operation where you have to be really mindful of where all the vehicles are surrounding you, especially in blind spots and such. Left and right turns. That's also a very tricky operation because you not only have to worry about oncoming vehicles that you might collide with, but also the cross traffic, the traffic that's also exchanged in the direction that's perpendicular to your flow of traffic. There's also platooning, which is very attractive for operations such as multiple semi-tractor trailers that are hauling goods across a country. For the sake of energy efficiency, it's often great to have these platoon of vehicles be in some sort of line driving together in order to minimize, in order to create aerodynamic flow. One truck would actually take the brunt of let's say, the air that it needs to move out of its way. But in the wake of that truck, you might have 3, 4, 5 other trucks driving in close formation, taking advantage of that slipstream that's being created by the first truck, and would translate into energy efficiency in terms of energy savings for the other vehicles. And then finally, collision avoidance. We already have that technology, but it's important to actually continue building up that technology in terms of making things more reliable, especially like right now we have collision avoidance technologies for vehicles in front of us, but how about in other directions as well? And perhaps even more of a warning that we don't have right now. Those technologies, again, just use line of sight sensor technologies. So as a result, 5G will actually enable the support of these different types of wireless connectivity needs by autonomous vehicles in order for them to operate on the road, such as in the conditions I just described. Therefore, 5G would support vehicle wireless connectivity as the ultimate sensor. right? Which would support beyond line of sight information gathering that is obtained at both the macroscopic, mesoscopic, and microscopic levels. So now let's look at the issue when employing this wireless connectivity as a form of sensing technologies for autonomous vehicles. And what we want to look at is really the case of when we have all vehicles relying on the wireless communications. Now, this is a problem. If it's like one or two vehicles on the road, not so bad. When we're talking about rush hour traffic conditions and hundreds of vehicles within several hundred meters of roadway, this actually does make a big problem, because the number one issue is, do we have sufficient wireless channel bandwidth to support all these wireless communication links for supporting this connectivity in order to support the sensory information needed for these autonomous vehicles to drive safely and reliably. In other words, if we want to support cellular, V2I, and V2V communications, we will require an extensive amount of wireless spectrum to make this all a reality. And because of this, because we need more of this wireless spectrum, especially in places like rush hour conditions and traffic conditions on major highways, what might happen, and this could be an issue, if we do not come up with a solution for this, what will happen is we might get the circumstances where the sensor's not getting information. Capacity has been met, there's no more bandwidth, and some vehicles are just left without any access to wireless information and must rely on the other sensors technology, which means that they don't have sort of the complete situational awareness or the extensive situational awareness that the other vehicles with wireless connectivity have, which makes for a less safe and less reliable situation. So, there are tricks that can be played in order to enable more of this wireless connectivity, especially when we're in a crunch, when we have lots of wireless systems all trying to access the spectrum all at the same time, and they all need this information. This is quite a challenging scenario. Okay, so what we need, is we need some sort of way of solving this, and for 5G. There is one technology that has been proposed that is quite core to its implementation, which is cognitive radio. So cognitive radio is a framework where wireless communication systems can sense the environment around it, including available wireless spectrum, and then intelligently make a decision about how to proceed in terms of configuring the radio to access that wireless spectrum, and how to set the parameters of the radio system to optimize that access, and then learn how to deal with new environments and conditions that have not been programmed into the radio platform. So it's great. The cognitive radio senses, adapts, and learns to its wireless environment. And what better way that we can apply cognitive radio than to the environment where we have, let's say, not enough wireless spectrum, or the wireless spectrum is extensively used by hundreds, maybe thousands of vehicular users in order to support their automated and autonomous self-driving operations. And one application, where cognitive radio can make wireless spectrum more accessible to lots of users at the same time to support these real-time, low-latency, vital communications is something called Vehicular Dynamic Spectrum Access. So Vehicular Dynamic Spectrum Access, or VDSA, is based on the dynamic spectrum access paradigm, which allows for secondary access to wireless spectrum in a dynamic manner such that spectral efficiency is maximized. So what does this mean? So suppose that the wireless spectrum is being used, but it's not being used 100% of the time. This channel, and that channel, and that channel, and that channel. So let's say you have 5, 10, 15, 100 channels. And at this moment, at this snapshot, all of them are being used. it can be said, and has been shown in several wireless measurement campaigns, that although, let's say, at one time instant, a set of wireless channels are all being used, it doesn't necessarily mean they're used continuously 100% across every channel all the time. What happens is a lot of wireless communications kind of act bursty. They might transmit at one time, and then there might be a big unoccupied state, like whatever wireless transmission needed to be done was done, and now it's quiet. So what dynamic spectrum access proposes is that in those spectrum holes, right, those available channels in those time instances, for another radio to temporarily transmit across those available channels across those time instances and get its information across. Now, what happens is what we're effectively doing is we're maximizing the utilization of every channel such that everybody has a chance to communicate information across from point A to point B. Okay? And cognitive radio is great because it senses. So it senses when channels are used and when channels are not used. It adapts. What it does is it says, oh, I can't transmit at this time. Oh, but that channel over there is going to be available right now. I'm going to go over there and transmit across that. And it learns. What it does is it observes channels over time and says, you know what? That channel is always being occupied, but that one is very, very infrequently occupied. I'm going to use that channel over there that's infrequently occupied. So cognitive radio is very well suited for maximizing the spectral efficiency that is achieved through vehicular dynamic spectrum access, or VDSA. So if we can leverage cognitive radio in 5G for automotive networks using the vehicular dynamic spectrum access paradigm, we can enable very efficient access to the wireless spectrum such that most or all vehicles can access the wireless spectrum to support their communications in order to, for the self-driving operations to be conducted safely and reliably, okay? And ensure that this very important sensor has information that's coming into it such that its situational awareness is always kept up to date. And 5G is going to be a very valuable and viable solution for future vehicular communications and networks and autonomous vehicle systems. This is going to be making it reliable. It's going to make it in order to support its access, immediate access to wireless spectrum, and as a result, so when we apply vehicular dynamic spectrum access through 5G, we get, again, that macroscopic viewpoint, the sort of the wide-ranging understanding of what road conditions are for tens of miles in all directions. We get the mesoscopic perspective, and that's achieved through V2I communications, vehicle-to-infrastructure communications for smart cities and Internet of Things and smart spaces. And then, very importantly, the V2V operation, the one that's so time-critical in terms of vehicles exchanging life-or-death information with each other in order to drive autonomously with no humans involved and drive safely such that everybody makes it home from work every day. So this, I hope you found this this description of how 5G can be used with cognitive radio and vehicular dynamic spectrum access in order to support large-scale wireless communications between autonomous vehicles in order for wireless connectivity to be the ultimate sensor for autonomous vehicles. And from this, we hope that this will truly make autonomous vehicles a reality, more so than what we see now with sort of the current set of sensors. So 5G is going to be critical in the next several years to make these autonomous vehicle systems a reality.
Thank you for listening to this edition of the IEEE 5G Transmissions Podcast. Discover more about the IEEE 5G initiative and inquire about participating in this effort by visiting our web portal at 5g.ieee.org.